carbon dioxide and methane on a habitable zone exoplanet? The James Webb Space Telescope unveils the mysteries of K2-18b, this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. As you may have heard, Los Angeles County in California has been deeply impacted by a series of ongoing wildfires. The Planetary Society's headquarters are located in Pasadena, California, and many of our staff live in this area. The wildfires have displaced several of our team members, and some are dealing with significant losses. We appreciate the patience of our members, supporters, and all of you, our Planetary Radio listeners, during this time. We hope that you're all doing well and that your loved ones are safe. For that reason, we're revisiting one of our most popular episodes of 2024 this week, but rest assured, we'll return next week with all new content. Today we're going to be diving into one of the most remarkable new exoplanet discoveries with the help of JWST, the James Webb Space Telescope. If you're a fan of the search for life or just cool exoplanets in general, you're in for a ride. JWST has detected signs of methane and carbon dioxide in the atmosphere of K2-18b. It's a discovery that could help reshape the way we think about the search for life beyond Earth and take our understanding of sub-Neptunes to the next level. Our special guest, Knicole Colón, is the Deputy Project Scientist for Exoplanet Science at JWST. She's going to give us all the details. Then stick around to the end for What's Up with Bruce Betts, the Chief Scientist of the Planetary Society. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Now, let's get into that spaceship of the imagination and journey to a world very much not like our own. About 100 light-years away in the direction of the constellation Leo the Lion is a world orbiting a red dwarf star called K2-18b. K2-18b is a sub-Neptune, which is a type of exoplanet with a size and a mass that's somewhere between terrestrial worlds like Earth and ice giants like Neptune. This one is about 8.6 times as massive as our planet and orbits within the habitable zone of its star. That's the area around the star where it's not too hot, not too cold for liquid water to exist on the surface. Sub-Neptunes are the most common type of exoplanet we've discovered in our galaxy, but you'll notice we don't have any in our solar system. These worlds are a profound mystery to us, but we're beginning to learn more with the help of space telescopes like Kepler, Hubble, and JWST. K2-18b was initially discovered using data from the Kepler Space Telescope, which was one of my favorites. It was a space-based observatory that was dedicated to searching for worlds outside of our solar system. But it wasn't until 2019 that this particular world truly made space news. A team at the Centre for Space Exochemistry Data at the University College London in the UK used data from the Hubble Space Telescope to analyze the atmospheric composition of K2-18b. They came away with a massive headline. NASA's Hubble finds water vapor on a habitable zone exoplanet for the first time. Or so we thought. A deeper analysis of the atmosphere of K2-18b would have to wait until the launch of the James Webb Space Telescope in 2021. An international collaboration led by Niku Madhusudan at the University of Cambridge used JWST to take another peek at K2-18b. And the plot thickened. With the help of JWST, their team detected something extraordinary. Methane, carbon dioxide, and potentially dimethyl sulfide, a compound that's primarily created on Earth by living creatures. Now, don't get too excited. We're not saying that there's life there, but that is a really cool finding. Our guest today is Dr. Knicole Colón. She's an astrophysicist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, USA. She's also the Deputy Project Scientist for Exoplanet Science for JWST and the Director of the Transiting Exoplanet Survey Satellite, or TESS's, Science Support Center. She previously worked as the Deputy Operations Project Scientist for the Hubble Space Telescope, too. Her research has always revolved around finding and characterizing exoplanets, but she has a special place in her heart for the wacky ones, like K2-18b. Hey, Knicole.
Hi. How are you?
Doing really well, and I'm really glad to have you on the show to talk about this because this is such an interesting world. And it's not the first time it's been in the news. I feel like I've been wanting to know more about this world literally for a few years now. You previously served as the Deputy Operations Project Scientist for the Hubble Space Telescope, so you're the perfect person to ask, did those first observations of K2-18b completely blow your mind?
In short, yes. But to answer in a longer way, it's fascinating because K2-18b, right, it's this relatively small planet. It's bigger than Earth, but it's not something that we have in our solar system. You know, it's a size that is unknown to us, essentially, even though it's very common. It's a mystery. And so we want to study the atmosphere and learn, okay, what the heck are these things made of? And that's where the Hubble Space Telescope came in with that first look. And we're like, wait a minute, this is really beautiful, actually, because we're so used to having to dig for such small signals when we study planetary atmospheres that are just really challenging to detect. And so seeing what looked like a really strong detection of a molecule that we could predict at the time, which we predicted was water, that was just, mind-blowing, like in a good way, because we predicted it and it was there.
I think what's cool about it, too, is that at the time, I remember reading that there was some suggestion that maybe there's methane on this world, but we just didn't really have the power to figure it out at that point. And now we have JWST, which is just blowing the lid off of exoplanet research. So it's got to be really cool to get in there and actually be able to make this detection.
Yeah, that's the powerful part of the Hubble Space Telescope, but also the limitation is it's able to give us these really first looks, a deep dive in the near infrared region of light where we could look for what is normally going to be a water absorption feature due to water in the planet's atmosphere. But the problem with planets like K2-18b, they're at this temperature where methane also comes into play at these wavelengths. And so there is this degeneracy that you have in the Hubble wavelength range. And so exactly with the James Webb Space Telescope, we could come in, expand that wavelength range, get really high precision data to look and see, okay, is it actually water, which is what we were looking for originally, or is it the methane? Which it turned out that, actually what we thought was water is most likely methane now. Mm-hmm. And that's why we do what we do.
Is there a potential for both things to be true?
There is a potential, yes. With the current combined data set, we saw Hubble saw something. We thought it was water because that was what the standard models predicted. It did also predict methane, but we had that degeneracy. We needed more data. So now we have more data. JWST tells us, okay, there's methane. That's great. But now we're actually going to be getting even more data with JWST in the future. So the story's not over yet. We think now methane is the dominant molecule and water is actually we'll call it non-significant. It's probably still there, but at much lower levels. And so that's something that with more JWST data, we'll be able to just basically get a more complete picture and see, okay, expand the wavelength range, getting more precise data and looking for more absorption features, seeing how they compare to the models exactly.
How did everyone react, the people that you're working with on this research? Was it surprising to them, or was it one of those punch the air, I totally knew it kind of situations?
I think it was pretty surprising, actually, because, we all, again, originally thought, oh, it's normal. It'll have some water and maybe carbon dioxide, some other carbon molecule. It probably will have methane too, but I think we were surprised to see just how methane dominant, we say, that the spectrum was. So many absorption features due to methane dominance. Not to mention the dimethyl sulfide hint. So we'll get there, But I think we were all surprised, especially because the star also that this planet orbits around, it's cooler than the sun, so it's more likely to have star spots that actually contain water itself. And so that added to the complication of the Hubble data originally, like, oh, is it really water from the planet, or could it be the stars contaminating the planet's spectrum that we're measuring? And actually, if it's not water, that's good, because then the star has less than an impact on the data that we're seeing, essentially.
And that's a great point and leads me to my next question, because I'm sure there are a lot of people out there who are unfamiliar with how we actually study these exoplanets' atmospheres. What kind of methods and what kind of instruments did you use to make this detection, and how does that relate to the star itself?
With these planets that we're studying, they orbit quite close to their star, relatively speaking. And so basically what that means is we are not able to actually resolve the planet directly. We're not taking a picture of the star, planet system, and we're not actually seeing a dot that is the planet. Instead, what we have to do is an indirect technique called the transit method. And this works out because literally the star and planet are aligned, in such a way that we can detect when the planet passes in front of the star and it blocks sunlight from the star. So we detect that overall dip in brightness. But on top of that, the planet has an atmosphere. So the atmosphere causes extra light from the star to be blocked. And that's how we can do this technique called transmission spectroscopy specifically. But what it is really is just measuring how the apparent depth of the planet plus its atmosphere changes as a function of wavelength of light. We can look for extra dips in brightness due to water absorbing in the, extra starlight in the atmosphere, or carbon dioxide or methane, whatever is in the atmosphere. It'll be there. It'll act as an opaque molecule. And so it'll block extra light from the star. And yeah, that's the technique we use. And it's the technique Hubble uses, JWST uses to study most of its planets. They do also study planets with direct imaging and do get pinpoints of light directly from the planet, but we haven't gotten there quite yet for planets in the so-called habitable zone, because they're just all still relatively close to their stars.
Yeah, we're going to need some serious instrumentation to make that work. But I think that's what's really cool about the fact that we're learning more about these sub-Neptunes as a population. They're not as small, so they're easier to study their atmospheres because they're just so poofy. So that gives us a really good opportunity.
Absolutely do.
Which spectrometer did you use on board the spacecraft to actually study this atmosphere?
So there are actually 4 total instruments on the telescope. And right now, the K2-18b has a couple instruments that were used, but more are coming. So basically, there's the NIRISS instrument, which is an acronym. I don't even remember it offhand. Every letter is an acronym. But it's the NIRISS instrument and the NIRSpec instrument that were used for this first K2-18b data. And then my understanding is that there's more data coming from the MIRI instrument, which actually goes further into the infrared than these other instruments do. So it provides even more additional wavelength coverage that we don't have access to with NIRISS and NIRSpec, which is good because then it adds also to what Hubble looked at before as well. And it just gets into more regions where we can look for different absorption features, or at least confirm like an independent confirmation of what we've already seen, even though it's the same planet, same telescope, but it's different wavelength of light.
Yeah, I was going to ask, will that different range of light allow us to just validate what we've already learned from your research, or might it tell us new things that we already don't know about the atmosphere?
I would say it's both, actually. So I like, the word validations. That's a great word to use because these molecules, they have absorption, like cross sections, we say, across a wide range of wavelengths. And so more than what the NIRISS and NIRSpec instruments cover. So that's why MIRI will be able to see additional features, absorption features from these molecules, and validate, again, the presence of what we've seen and even the abundance. Because when we look at these features and we see like an absorption feature, that's a detection, but actually then we do extra work and models to extract out like the abundance of those molecules in the atmosphere. And so having the extra wavelength coverage will validate both the detection and abundance measurements. And then, just literally anytime we look at a new wavelength, especially with JWST data, for any exoplanet lately, it seems like every data set we're getting some new feature that, maybe we're not necessarily expecting to see. We can confirm it with models and all that. We're not seeing anything like too unexpected in a sense, but we are seeing things that maybe we didn't realize we'd see so easily with JWST, just because the telescope's working so well that like every data set's like, oh wow, we could see that just like that.
Really, though, I was having a conversation with one of my coworkers the other day about how when he was younger, we didn't even think they were going to be able to detect exoplanets at all. Then by the time I reached college, we were just beginning to find exoplanets. We were doing it one transit at a time. Then comes Kepler and TESS and all of these other telescopes. Now we're sitting on 5,500 exoplanets plus.
Yes.
And now we can look at their atmospheres and see clearly what's going on with them all this distance away. I wish people could appreciate how absolutely wild it is, how much progress we've made in the last few decades.
Yeah, it's amazing. I remember when I started graduate school and I wrote my first paper as a grad student. In the introduction, you always talk about the current state of exoplanets. And I think it was literally fewer than 20 transiting planets at the time. And I could tell you something about every single one of them. You know, I knew all their names, their properties, right? Everything. With 5,500 plus planets, I can't do that now. There's no way.
But, you know, that gives you the opportunity to specialize. And I understand, like, you're angling for the worlds that are ones that we really don't encounter in our solar system, which is the most interesting group.
Yeah, I think it's fun.
How many transits of this world did we need in order to make these detections?
So with JWST, the thing with all these first results that are coming out, a lot of them are first looks. So we get just a couple transits of a single planet to get the first data set. And then we most likely will have astronomers propose to follow the targets up once they have that first look. And so that's what happened here with K2-18b, where there were 2 different transits observed, but it was only one with each of the instruments. One transit with the nearest instrument and then one with the near spec instrument. And it's actually quite impressive, you know, that we only had these 2 data sets and already see so much evidence of so much information contained in the data.
Yeah, unfortunately, everyone and their mom and the kitchen sink wants to be using JWST because it's such a powerful telescope. So we're limited on what we can do with these first looks. And even then, almost every single one of these exoplanet studies has just discovered things that we did not expect to happen. It's actually really impressive.
Absolutely. And keep in mind, too, as much as we would like, JWST, you know, it studies some things that aren't exoplanets, too. We can't use all the time.
Unfortunately, we just need 16 JWSTs is really what we need.
That's right. That would be amazing.
I know there's some indication that this world might be a Hycean exoplanet. What does that mean?
Yeah, this is a weird, I say weird thing because it's a newer concept. And so it's a little strange to wrap your mind around because it initially boils down to the fact that it's a like super Earth / sub-Neptune sized planet. So what that means is these Hycean worlds are like something between 1 to 4 times the size of Earth. They're not quite Earth size, they're bigger, but they're not quite Neptune size, they're smaller. And for the solar system, we don't have anything like that. They're brand new to us, but more than just their size, they also have appropriate masses to have the right density to basically have a substantial rocky core, but also substantial surface ocean, and then having some type of atmosphere, likely an extended hydrogen-rich atmosphere. So there's a lot of hydrogen, there's presumably a large water ocean, but also a dense rocky core. So they're very dense but fluffy. So fluffy in that they have an atmosphere that we can study with the whole transmission spectroscopy technique. So they're interesting targets because Earth is considered, it's obviously got a dense rocky core, but its atmosphere is very thin, relatively speaking. And these Hycean worlds are something that are thought to have not just a super dense atmosphere, again, like Jupiter or Saturn or Neptune would have, but something that is more like Earth, but just a whole new world, literally,
right.
if you can imagine.
It's hard to imagine because it's so outside of our understanding. We don't even know much about Neptune and Uranus, given that we've only flown a spacecraft by them once in our entire history of exploring space. So we're already very limited there in our understanding of these ice giants. Then you throw in a world like this that's a sub-Neptune. We've never seen anything like it. And then detections of methane and potentially water. It's so outside of what we know and understand that it's a perfect target for expanding our understanding, not just of worlds, but in the search for life particularly.
Yeah, if we are searching for life, that's what we want. We do, even if we don't mean to do it, we're doing it all the time. So it's a matter of, expanding our horizons a bit. Like, we know of Earth having life. Obviously, we're here, we're talking on this podcast. There's life here. But that's life as we know it, right? So we do have to think outside the box. What is life as we don't know it? And that's where astronomers have postulated this new population of planets that could be potentially habitable, even though they are in this unique size, mass density range. And all these observations are really the first step, starting with Hubble to JWST. They're the first step in saying, okay, does the atmosphere composition match the predicted models and all that for this type of world? And how does it all fit in? Is this still a Hycean planet? I think, the evidence is still there, but there's, like we mentioned, more JWST data going to come, and I'm sure even more beyond what's planned already.
Oh, I'm hoping, because this is a weird one. It deserves a lot of observations to try to understand this, just because anytime you stumble across a world like this, it's like a needle in a beautiful haystack that goes on for infinity. I did want to ask, though, sub-Neptunes are the most common type of world that we have detected in our galaxy. Is that a consequence of our detection methods, or is it actually the case that it's the most common type of world?
So most of these worlds, in general, most exoplanets have been discovered with the transit technique. In that way, we are biased to systems where the planet is literally aligned to cross in front of the star from our point of view. I guess the other bias there is those planets preferentially orbit closer to their star too, because that just increases the probability that we'll detect them. But that said, there does seem to be a lack of giant Jupiter-sized planets. Those would be the easiest to detect by far. Those are the first ones detected by any detection method, essentially, or at least around a sun-like star. And you would think, okay, if giant planets are the most common, then that would be the most dominant population we'd see, even ignoring detection biases, right? Otherwise, it's just if giant planets are there, they're the easiest to detect. But instead, we're finding things that are smaller, right? Between 1 to 4 Earth size as the most populous. I think that was a surprise, because we wouldn't have predicted that, again, based on the solar system, because that's what we know. But we also didn't predict that we would find giant hot Jupiters orbiting 3 days around their star. So that also broke things. In a sense, finding so many super Earths, sub-Neptunes, mini Neptunes, whatever you want to call them, I guess it's not that surprising in the end, because we are finding all kinds of extreme scenarios to be out there. The Kepler mission, right, is the one that basically broke this door open with its survey. And that's the one that's found the most transiting planets so far. And, it's looking like, tests. So the test mission's following up, doing an all-sky survey, mostly around nearby bright stars. And it's also equally finding lots of more sub-Neptunes, mini Neptunes. So, the story holds, basically, no matter where you look in the sky.
That's so weird. It's so wacky.
Weird. Yeah. I don't know how to explain it, but people are thinking about it. Certainly. I'm not a theorist, I don't do planet formation models or anything like that, but people definitely are thinking hard about this.
Mm-hmm. You spoke a little bit about this earlier, but what do we think this world might be like? It might have a bit of a hydrogen atmosphere, but what are the variations here on what it might be like inside and what it might be like with a water ocean?
I guess we know that there's a lot of methane. So the interesting thing is, I think, so we see a lot of methane, right? Or we see a lot of methane absorption and strong detection there. But the fact that the JWST data basically didn't find strong evidence of water in the atmosphere, that could indicate a couple things, right? It could indicate that maybe there is no ocean. There's no water evaporating on a regular cycle, or maybe the ocean is not water, could be something else. So those are a couple of factors. Or maybe the ocean is frozen solid and it's also not evaporating into the atmosphere and having a lot of water transition and a water cycle like we do here on Earth. So yeah, it could mean there's no ocean, could mean it's frozen. It could mean that maybe it's an ocean like liquid methane or liquid something else.
Yeah, something like we see on Titan. That would be crazy.
Exactly. So there's all these scenarios that you can imagine that I think are especially driven by the lack of that significant water detection, because then you can play those games, right? Okay, we see methane and carbon dioxide. So how does that fold into what could the surface actually be like? And yeah, it is fascinating to think about based on that kind of lack of water.
We'll be right back with the rest of my interview with Knicole Colón after this short break.
Hi, I'm Asa Stahl, science editor from the Planetary Society. Stargazing is our everyday window onto the universe, but only if you know how to explore the night sky. Join me in a new online course from the Planetary Society, where we'll discover the wonders waiting to be seen overhead. No matter where you live or whether you own a telescope, this how-to guide will transform the stars into a clear view of the universe. You'll learn practical skills for parsing the night sky, get tips on how to see the best possible views, and hear the latest from professional astronomy communicators on how to help others fall in love with stargazing. Everyone from newbies to space nerds are welcome. Remember, this exclusive course is available only to Planetary Society members in our member community. So join us today at planetary.org/membership. That's planetary.org/membership.
Before we get into the intense, weird chemistry of this world, I wanted to ask a little bit about its star and kind of the situation going on in that star system, because it's a smaller red dwarf star, but those stars tend to be, as you said, a little spicy in their younger years, right? They flare up a lot and sometimes create these really potentially hostile environments for at least creatures like us. So is there any indication that's actually the situation in this system and that it's creating this kind of volatile, hostile situation?
I would say, luckily, not terribly hostile.
Mm-hmm. That's good news.
So you're right, though, that this star, it's cooler than the sun. It's smaller than the sun. And as I mentioned, a lot of times these stars tend to be more active, as we say. And so that means they could flare more. So our sun has flares and emits radiation all the time, like having star spots come in and out and evolve over time. And these stars, like K2-18, they do have similar episodes of flares and spots that grow and evolve and dissipate over time. But just by their nature, that tends to happen more often than it does on the sun. But yes, as far as I'm aware, this star is relatively well behaved. It's not excessively flaring, emitting crazy amounts of radiation. And that is especially important to think about just because we mentioned with planets like this, it orbits relatively close to its star. It's in the habitable zone, but the habitable zone is shrunken in compared to how we are in the solar system. We're in our habitable zone around our star, but we take a year to orbit around our star. This planet orbits much closer. In any case, this planet seems to be relatively safe in the grand scheme of things.
That's good. I mean, what's interesting about this for me is that this world is close enough to its star, but it's fairly big. So chances are it has a global magnetic field or something like that. And it's got a big old atmosphere on it. So we know it hasn't blown away just yet. So that's pretty useful to know. I think that we're really about not just exploring worlds, but trying to seek the familiar out there, particularly in the case of life. And what's cool about this for me is that if this is in fact like a Hycean world, it's not around too spicy of a star, right? That's really useful to know because this could be a good target to explore the potential for life on these kinds of sub-Neptunes. Because right now we're very limited in our human-centric way of thinking about this. Even in our own solar system, we're looking at these terrestrial worlds that's been massively expanded by the idea of subsurface oceans. But add in that these kinds of worlds, and who even knows what's going on out there? It makes me feel like we're on the cusp of something so broad that we just don't even know how to understand yet. Absolutely.
And just to add to that, if we did want to think about life as we know it, let's say, and think about, okay, what Earth-sized planets are there around sun-like stars? There's not many that we've discovered yet. So that's another reason why, systems like K2-18 that orbit a bit closer into their star and they orbit stars relatively nearby, they make really great targets to study because they just are more common than at least Earth-like planets around sun-like stars so far. Mostly because we haven't, been looking for exoplanets long enough to find Earth-like planets around sun-like stars. So there is that bias. But that's fine if we study what we know and study, again, life as we don't know it. That's totally fine. We just want to understand, okay, what is the scope of the universe we're dealing with here?
And how cool is that we're just a few years out from the Dragonfly mission going off to Titan. If there's, in fact, a bunch of methane on this world, then maybe we can learn more about the conditions on a world like Titan. It's much smaller, but if there are seas of methane and indications of organic components, we can finally begin to compare these things, even though they're very different. But, you use what you got.
Oh, yes, absolutely. And that's very important because we astronomers collectively have been looking at these types of planets, like where's the methane? They have the right temperature. They should have lots of methane, just like the planets in our solar system. And we hadn't really seen that until this system. So that is finally maybe a puzzle piece solved, right?
And clearly you and I are excited about methane, but we should probably explain why that's such an exciting thing to discover on a world. And why are we so jazzed about methane and carbon dioxide on this planet?
I'll start first by saying, we've always looked for water first because that we think is essential to life. And we want to look for life. And so we're like, okay, we need water to survive. Let's look for that. But if you want to think even at the most basic level, methane, carbon dioxide, water, they all contain carbon. Water doesn't contain carbon, but collectively they contain carbon, hydrogen, oxygen. And these three individual molecules are what we refer to as the building blocks of life. This is, again, carbon-based life as we know it. But these are like three essential elements out there that we expect are essential to combine, to come together, to form life, to form hospitable atmospheres, make up oceans and water, bodies of water, all of that. And these molecules are essential in that respect. Of course, there is a separate tie-in that methane or other molecules can be also byproducts of life itself, even if it's artificially produced, even if it's technology producing these molecules. So it's kind of like both come together where we have the basic building blocks of life, carbon, hydrogen, oxygen. We want to look for those molecules or molecules that contain those elements because that is essential. But then we also know what are the key byproducts of, again, life as we know it, but that is where things like methane come in.
I'm sure some of our listeners remember a few years ago, there was the potential detection of methane on Mars. There's a lot of study left to be done with that, so don't get too excited just yet. But part of why that's so exciting, at least to me, is that on Earth, methane has this short lifetime. And it's specifically because of the interactions with other chemicals in our atmosphere. I think I am not a chemist personally. I studied astrophysics instead, but I believe it's the UV light from the sun is photodissociating water, and then some of the byproducts are then destroying the methane, right? So all of those situations there could be something that might be happening on this world as well. It's a smaller star, so less UV light, but there is a potential that this methane could be breaking apart as well and have a short lifetime, which means that there's got to be something producing it. And
yeah. Mm-hmm.
I don't know what that is, but whatever it is, it could be some kind of geologic thing, but also could be an indicator of life.
Yeah. And just to pick up on something you mentioned too about the star, something I honestly find hard to wrap around, but because the star is, again, different than the sun, it actually does emit more ultraviolet radiation than the sun does.
Really?
Because it does depend on the star again, but in this case, we're not surprising if there are effects of radiation, extra effects of radiation, I should say, compared to the sun. And that really comes into play too, especially if it has some of these energetic flares. Now, we don't really see, again, evidence of that too much. So we're probably safe, and we probably aren't dealing with the massive effects of this radiation. Like you said, that there's obviously an atmosphere there. But it is interesting to think about, is there a lot of this photochemistry happening in the atmosphere because the star is different than the sun? And so is there other or extra photochemical processes we should be considering and looking for photochemical byproducts, especially? Yeah, I don't know the answer, but I know that it's definitely something people are thinking about as we study a lot of these types of M-dwarf stars.
And I mean, methane isn't a 100% indication of life. We find it all over the place. But I think what's funny about this is I was learning more about this world and looking at the spectra, and I'm going to add an image of the spectra of this on the website for this episode of Planetary Radio so people can look at it. If you look at the right side, you'll notice that there's this detection potentially of something called dimethyl sulfide. And it's so funny to me because I feel like this was the result that actually made the hair on my arm stand on end. Because on Earth, as far as I understand it, the only thing that creates this specific molecule is life. And it's mostly like phytoplankton in the ocean. Did that super surprise you, or are there processes that I'm unaware of that could be creating that?
Well, firstly, I am not an astrobiologist, I will say, and I was like, what is dimethyl sulfide? When I first saw this, I was like, wait, what did we see? How? Oh my gosh, this is for real. I knew that people were predicting that we might be able to see different, what we call these biosignatures with JWST, but I didn't expect it, A, so soon into the mission, or
Wow.
B, just so easily. Yeah, but this dimethyl sulfide, that is absolutely my understanding that it's only the byproduct of some kind of plankton. Yeah, it's very interesting. The data are really showing a lot of surprises, as we said already, with so much methane, carbon dioxide, not much water. And now you're adding like this hint at this dimethyl sulfide, which it's, again, the first look. This is where that MIRI data is going to come into play, especially to validate the signal, because it's like a big teaser right now, like all of this. Yeah, it was very surprising to see this result.
I mean, it might be one of those situations again where it's like you think it's water vapor, it turns out to be methane, right? Maybe it's not actually what we think it is. But if it was, that would be so cool. Such an amazing thing to find. So I'm glad that we're going to have follow-up observations on this, because that for me was the headline that stood out, but you can't really write, they found dimethyl sulfide in the opening of your article. You can, but you might scare people.
That's right. It is, a really interesting result. This, again, a lot of these like sub-Neptunes have been mysterious and have wanted to hold on to their secrets. And we go to look at their atmospheres and we see flat spectra because their atmospheres are too opaque. They're too thick. We aren't able to detect anything. They probably have just thick clouds, like, again, Neptune or Uranus. And so we just can't dig in and see, okay, what is in the atmosphere, because it's just, we don't have the right tools. Even with JWST, unfortunately, it's just the planets themselves are difficult. And that's where this result comes in. Again, it's obviously not covered in a thick cloud layer, because that would obscure our observations. So that's a good thing. So yeah, now we see these other bumps and wiggles that are just really intriguing.
Are we going to be trying to study the clouds on this world? Because I know we've managed to do that with some other brown dwarfs.
Yeah, there's, people are able to do all kinds of studies depending on the wavelength that you're looking at. And with the MIRI data coming in, I believe that's being taken early 2024. That will extend further into the infrared. But with the current data in hand, that extends towards the optical. And that's where, when you have the whole wavelength range, you can really break degeneracies further and say, okay, these are the absorption features that we're seeing from the different molecules, but then maybe their amplitude of the feature is not as high as the models would predict because there's a cloud layer damping the feature. So that is something where when you have the infrared data, that is less likely to be obscured by clouds because we're looking like deeper in the atmosphere nominally. That is where you can break those degeneracies. And so having that as an anchor essentially helps to decipher better like anything going on towards the optical range. Yeah, so I'm really interested to see basically what happens when we get all the data together and people run their models, run their magic.
I did want to ask about one thing that I don't know a lot about. And when I was reading about this, one of the articles I read said that there was less ammonia in the atmosphere than we expected. And I wanted to know what set that expectation or why that's surprising.
So when you look at between the temperature of the planet and the density and even considering the star and the types of the literal radiation environment you're just in, it boils down to, okay, you expect some key molecules to come into play just based on the chemistry that you assume the atmosphere has been dealing with over its lifetime. And so, yeah, ammonia would be one of these that for this specific type of planet would be predicted to be dominant. Yeah, it's surprising. But that's honestly why we do what we do. To see, okay, we make all these predictions, but we don't know until we actually look. And it doesn't mean we're wrong. It's just we're refining our predictions and our models.
I'm biased. We're biased, but I feel like just space exploration in general and the exploration of exoplanets has got to be one of the most exciting fields in science right now. All science is being accelerated by new technologies, but we're really at a golden age right now where we're just constantly tripping over things we didn't expect.
There's a lot more to come, right?
Yeah.
So JWST's been, I guess right now we're coming up on our 2-year launch anniversary pretty soon, which is crazy how time flies.
It really is. I remember that Christmas. We stayed up all night to watch that launch.
That's right. Yeah. I don't think I slept that night either.
Yeah.
But yeah, it's, so this is like the tip of the iceberg, right? All these results we're finding for exoplanets. And honestly, we're still finding exoplanets all the time. A lot of them or some of them will be great targets for JWST. And so that's where all the research astronomers are doing essentially, interplays, because we just leverage all our resources to do as much as we can while we have them, because sadly, spacecraft don't last forever. We do what we can to maximize what we can learn and even start planning for the next missions ahead. So.
We're going to need more of them because we're just literally at the tip of the iceberg. We're all excited about 5,500 worlds, but that's literally nothing compared to how many worlds are out there. Before I let you go, though, I mean, I know you can't possibly know the name of every single exoplanet, but other than K2-18b, are there other exoplanets that you're really excited for JWST to take a look at?
Oh, yeah. I mean, there are many. So I will say that. So actually, one of them, it's not a sibling to K2-18b, but it's actually K2-22b. So it was discovered shortly after K2-18b is the point. They're kind of related. But in any case, it's a rocky planet. But the cool thing about this planet is we expect it's a bare rock because it's actually disintegrating. So it's coming apart. And we've seen evidence of this. There's a tail essentially of rocky material outflowing from the planet. And so JWST is going to take a look at this planet, should be early 2024, and it's going to basically be trying to measure the composition of the rocky material that is outflowing, so the dusty grains. So we're literally attempting to measure what the interior of a planet, an exoplanet, is made of, which is crazy. So not
it's like the biggest comet tail ever.
Right.
Wow.
Yeah. So that's something that's really cool. And it's around an M dwarf, just like similar to K2-18. So like they're kind of siblings in that sense, but K2-18 just was not surviving its star. It just orbits way too close.
That is so cool. I knew you'd have a great answer for that since you study all the weird ones. That's awesome.
I love it. Yeah.
Well, thanks for joining me, Knicole, and telling us more about this world. And I'm sure there's a lot more to come in the next year as we begin doing follow-up observations and analyzing even deeper. So when it gets even weirder, I'd love to talk to you again.
Sounds good. Yeah, just keep looking out. There's so much coming.
Thanks. It's absolutely amazing to think about what might be out there in this universe. It's filled to the brim with countless worlds that are just waiting for us to explore them. And you and I get to live in a time when our exoplanetary adventure is just beginning. You never know what we might discover in our lifetimes, and that is so cool. But in the meantime, let's check in with Bruce Betts, the chief scientist of the Planetary Society, for What's Up. Hey, Bruce. Happy New Year.
Howdy and Happy New Year.
I'm really glad to be back. Being sick around New Year is always such a bummer because I didn't get to go out and see any fireworks or anything, but that's all right.
We got to hear plenty of them because they just explode near our house.
Now, living in Los Angeles is just one of those things. Anytime there's a big celebration, the whole city just erupts in fireworks, despite them being illegal.
Yeah, it's really rather impressive how many. I mean, there were some huge ones this year. Enormous. And, yeah, dog not happy. Okay.
Not happy. But, it's funny. Anytime I'm like majorly sick, it's such a silly thing to think about. But I keep thinking about like, what would happen if we ever made first contact with other alien creatures and we couldn't hang out with them because we'd get them sick? Like, I know there's a lot of complexity to the way that we transmit diseases between species and stuff like that. But anytime I'm sick, I just think to myself, I'm probably never going to get to hug an extraterrestrial.
God, your brain is amazing. And this is when you're not fevered out.
It's true. It's chaotic space madness in there.
Strangely, I feel badly that you don't think you'll be able to hug an extraterrestrial. And that is not a thought I would ever have.
But, in happier news, I got a lot of really beautiful, heartfelt messages from people during the week that I was sick. And I just want to say thank you to everyone that sent me emails or poetry or the people that wrote messages in our member community. It made me so happy and I feel so appreciated. So thank you.
Did you get the flowers I sent?
No.
Oh, how unusual and weird. What else you got?
One of the people that wrote me during this week was Dale Davis, or Dale DeVaz, forgive me if I'm mispronouncing that, from Oregon, USA, who wrote best wishes on my recovery, but also said that he's a new member because of listening to Planetary Radio, and that he's sure it's probably one of the reasons he'll stick around for a while. So that's high praise for us. Also, one of us.
That's awesome. And hey, everybody, come on, join us. Be one of us. And we promise you will not get fever dreams like Sarah's had just for joining. You will find a wealth of happiness.
I just had such a really fun time talking to Knicole about this planet about this exoplanet, because I feel like sub-Neptunes are just so weird. I'm sure they're not as weird as I think they are. They're just completely outside of my experience learning about our solar system. We don't have any sub-Neptunes in our solar system. So knowing there's so many of them out there just begs the question, like, what kind of other weird worlds are we just so unaware of?
I don't know. You got your super Earths and your sub-Neptunes, and I feel like I'm trying to out-weird you now. And
maybe. What about like mirror planets or like crystalline planets or
you win. You win. Mirror planets?
Yeah, what if they're just like covered in shiny metals or I don't know. But yeah, that's my brain when I'm sick. I'm just thinking about weird stuff all day.
All right. Well, I got to reset. So Venus has really long days, or days and nights, depending on how you look at the word day. Long daytime, long nighttime. And you can kind of get what it means when you say it in days, but let's take a little jaunt into a scale time model where the Earth spins around in 1 minute. The Earth spins around in 1 minute. Venus spins around in about 2 hours.
Yikes. That's really slow.
Considering it's actually like 117 days. That's the day like we call 24 hours where you're turning back and get the sun back in the same part of the sky. So what normal people call a day. There you go.
Do we have any idea why it rotates so slowly?
The basic theory usually involves giant impact early in formation that ended up causing the rotation, because it also rotates the opposite of everyone else in the solar system. Well, not Uranus is on its side and just a baffling beast of its own, but other than that, So it rotates slowly the opposite direction. If you could see the sun, which you can't from the surface, but you can tell if it's daylight, it would rise in the west and set in the east. And it's all, at least as far as I'm aware, it's still big impact, just tilted that sucker, changed momentum, got wiggy. If there's a new theory that I've missed, like involving crashing into a mirror planet, let me know.
That's why it's going backwards. Mirror world.
Dude.
All right, we can end it there.
All right, everybody, go out there, look up in the night sky, and think of a mirror planet and what you would see if you looked into the mirror. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with even more space science and exploration. You can help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts. Your feedback not only brightens our day, but also helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members from all over this beautiful planet. You can join us and help to build a bright future full of mind-blowing discoveries at planetary.org/join. Mark Alverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.